really fantastic metals analyst, and I was there primarily not to do metals testing or anything with the method development. I'm not even close to a metals expert, probably not even a good metals analyst, so I was there working on other projects, but of course we were communicating, and the metal scientist sort of was running into some issues. So at some point I thought, well, maybe I can help, and then I'll tell you what happened. So nothing too thrilling in terms of what we were working on here. Primarily we were focused on flour. The scheme was just to do subsampling, comminution, and microwave digestion, then analysis with an ICP-MS, and then we were also responsible for setting up an appropriate calibration and quality control scheme and building that into a batch structure for the client. So the client had sort of purchased a canned method, and that came certainly with the parameters for the ICP-MS, some initial training. I believe there was a little bit of information about calibration, and then it did have parameters for the microwave digestion. Unfortunately, and I'm sure some people have experienced this as well, there was, in terms of a supply issue, the digester that was built into sort of this application note was unavailable for quick delivery, so an alternative was purchased, and so there was a little bit of work that actually had to be done into building that out and making sure that that worked well. And then of course the calibration really had to kind of be customized and built around the particular regulations in that area. So the metals we were testing for listed here: arsenic, cadmium, mercury, lead. The canned method came with these 3 internal standards, and ultimately the calibration ended up being, well, it uses the 0-point metals up to about 50 ppb injection concentration, and not every one of these metals was tested along that range. Everything was really bracketed around the specific regulatory limits of each one of the metals. So that worked, was probably several weeks, and then we were continuing to vet the method once all of the basics were functioning well. And so that involved now doing some spike recovery in matrix and making sure that worked. We wanted to confirm that the curve was repeatable, and then of course we had to design and test the quality control measures, set criteria, make recommendations on that, and then the final stage was to do some preliminary training and sort of mock batches, because there's a lot more than just running the method. You actually have to figure out the best workflow to run a batch and pass a batch. So made it through the spike recovery matrix. That all seemed to sort out pretty well. No issues there. Curve was repeatable, didn't have any issues with curve models or accuracy or anything like that. So cruising along. Next up was the batch and the QC setup. So this particular analyst decided to put in several measures. So method blank, that's just simply carried through the entire procedure. Diluent blank, sometimes outside of metals may be called a solvent blank. So that's just your solvent or your diluent that's not carried through the procedure. A matrix spike and a matrix spike duplicate. So that would be a sample, so a matrix sample that was spiked with a known amount, and you do duplicates of those. The suggested criteria for that was 70 to 130% recovery. Then what was set up was an initial calibration verification standard in ICV. So this is typically run, or in this scheme, it was run after the calibration curve. This would be generated from a second source. So when you buy your certified reference materials, your chemical standards, you're typically going to buy from, vendor X. And in order to have some quality control, you would actually purchase similar product from a different vendor, so you can sort of cross compare and have a check on that. So much depends on those CRMs and your calibrations and QCs. So the ICV would be a second source or a different lot from that was used to actually generate the calibration curve. And then the criteria suggested here was 90 to 100% accuracy. And then we move on to our continuing calibration verification standards, CCVs. In this scheme, it was recommended to analyze after every 10 sample injections, and generally speaking, you could use one, or you can use more than one. This kind of depends on your fit for purpose, maybe the range of your analytes, or the span of the regulatory limits of your analytes. And again, the criteria here was 90 to 110 accuracy. Okay, so the batch structure essentially started with blank, calibrators, ICV, CCV, method blank, recovery checks or the matrix spikes, and then some sample injections. Then you would do your CCV, sample injection, CCV, sample injection, CCV, sample injections, and on and on and on. Okay, so the quality control batch was designed and tested, and everything okay. Then there was a little bit of a break, maybe a week or two, where we were kind of waiting to get to the point where we were going to kind of finalize this portion, do a little bit of basic training, finalize, with some mock batches, and be done with the project. So of course, as soon as we started up, or the analyst started up the mock batches and the training, there were some arsenic failures. So it was really unfortunate because the entire time during the method development and the vetting of the method that had occurred previously, this just never was an issue. So it was really kind of surprising and obviously not what you want to happen when you think you're kind of tying up a project. Okay, so obviously the first thing to look at, and he kind of immediately identified, is really just the only issue, arsenic, right? I mean, you sort of have a flag and you see that there's failures, but go back and look and see, like, is anything close to failing? Kind of root into the data a little bit and just make sure that we really only have one problem analyte. And the second big question, which is something I kind of constantly look at, and even they're extremely valuable, is to look for trends. That's part of the reason why trending is recommended and a really popular way to do ongoing quality assurance and quality control, and even also sort of part of good practices in terms of ISO 17025. So we want to know if there's any trends. We definitely know it's only arsenic. He confirmed that, and now we have to dig into the data a little bit more. So again, our batch starts up here. We've got some calibrators, ICV, CCV, and then our samples. So this is actually the first injection to the last injection. So calibrators, no issues, ICV, CCV1, CCV2, and then we start getting failures. Okay, so we're starting to at least see a difference here. We have passing and then we go to failing. It's not a miss, it's not pass, fail, or some sort of some more randomized trend. We are seeing the first part of the batch is passing, the second part of the batch is failing. But we need to dig in a little bit deeper and see if there's anything else other than we have passing and then we have failing. So we're just going to take a look at these samples here. And I'm going to go ahead and just from the listing, go ahead and remove the sample so we can just focus on looking at the CCV, the ICV and the CCV data just a little bit more clearly. Okay, so it's the same table here. So remember first injection, last injection, and our QC samples that have run throughout the batch. Again, as a reminder, these are passing. These are failing because the criteria for accuracy here is 90 to 110. At least that's the recommendation that the scientists have given. Okay, so it's not too hard to tell that we actually have not just a passing and failing, we actually have a downward trend when we look at this data. So that's to know. It's the same table. Here's the expected concentration in this pink line. Sometimes even though you can eyeball this and the accuracy makes it pretty easy to sort of see where you start and where you end, but sometimes visually it's nice to see what the data actually plots out as, because it gives you a little bit of a visual in terms of magnitude. And because the x-axis is also the injection number, it is a good reminder that you do have 10 injections essentially in between these points. So there's more going on than just these CCVs running, right after one another. Okay, only arsenic, and we definitely have trends downward in across the batch for our CCVs. So we're building up some information. Okay, so at this point we thought, okay, it's really clear. The arsenic is showing that that over time something is happening to it, and we're getting back a lower and lower concentration. Ultimately, it's crossing over that 90%, which would be the low end of our pass accuracy, and so we're passing over into failing. So the idea was we're losing it somewhere. And so at this point, I was kind of hearing the discussions and bouncing some ideas back and forth. But again, because I'm not a metals person, I'm not that helpful in terms of maybe troubleshooting instrumentation and really understanding things like stability of the standards and all of those types of things. So here's just a list of, I think, everything I can remember that the scientist that was working on this tried. So remaking the standards from, previously used CRM chemical standard stock. So was there something going on maybe in the stock, or was it particularly old? So trying that is one of the first things he did. Then CCVs and calibration standards were actually made from a new CRM material just to eliminate that as a cause. And then, none of this is really fixing the issue. So the, batch was basically set up to retest, and he was physically watching and monitoring the needle, the pump, and the tubing to see if there was anything in terms of the mechanics of that could be potentially be happening. Kind of went back and just confirmed, would there be any sort of loss or adsorption or something on any of the labware that maybe was being used that was overlooked initially when the workflow was set up. And then, one theory was, well, does it have something to do with it's kind of settling out, or is there something where the solution isn't remaining, homogeneous while it's sitting there? And so he even, before sample introduction for each of the CCVs was actually sort of mixing it manually, just before introduction. Still, that didn't help. And then kind of moved on to cleaning the instrument, the cones, some of the other parts. I believe new cones were considered, and I think they were swapped out at some point. The tubing was changed, and then it was a new facility, and there were some fairly large swings in the room temperature at the time. HVAC, some issues cropped up, and maybe the AC wasn't working as well as it needed to on certain days. So that was a consideration as well. And then, of course, reached out to someone that has expertise in metals analysis and sort of got some advice from that person. So this was a fair amount of work, trying to troubleshoot, and unfortunately, nothing really helped. And so this was probably about a week and a half of work. Obviously, that's a significant amount of time on a project. There were some supplies that were used, some new supplies that were purchased, and this poor scientist was a little bit dejected because he had been troubleshooting and working really hard to sort out the issue, but really we're still seeing some of those failures. Okay, so at that point I said, okay, I mean, I can help you. I don't know if I can be that much help, but we can give it a shot. So the first thing he showed me here was this data. So the expected concentration and what the value that was returned, and of course the failures. And so I was like, okay, I get that. And I said, but these numbers are not, that's not really the raw data, right? So I said, I want to see the raw data. These values are generated from a calibration model. That calibration model is, in this particular case, was built on the signal and concentrations of the analyte as well as the internal standards. Those are then essentially built on the signal of the analyte and the signal of the internal standard. So I said, that's what I want to look at. I just want to go to the raw data, and I want to look at the actual signal. So, so this data was pulled, and you can see here, if you start looking 2547, 2398, you can actually see that this is not unexpected because we knew that the concentration was also going down. So we're seeing the signal go down, and so that all makes sense. And then we get to the internal standard, and one thing that immediately sort of caught my eye was that, well, this is actually increasing. So that's hello. Again, I like to look at plots, and so what this actually, one of the things this helped me look at as soon as we saw this, is that, we know that arsenic has this downward trend, and these are kind of, I did scale these to be sort of relative percentage wise to the first point, and then this is for the internal standard. And so just visually, what we were able to see without doing a whole lot of calculating was that this upward trend was greater in magnitude than this downward trend. So it's just something to kind of keep in mind because the internal standard is quote unquote correcting. And so those corrections would be of a larger magnitude because of this trend. Okay, not good to have opposite trending between your analyte and your internal standard. Typically, this was the first time that the internal standard was actually looked at. This was the first time that he realized that potentially the internal standard was an issue and potentially a really large issue. Okay, so you may be self, okay, well, everything you're looking at is the same concentration in terms of the analytes, or the analyte's the same concentration for every data file you're looking at. The response factor or the internal standard is the same concentration. So why are you even looking at the response factor at all? Because you can see if you look at the response factor versus the counts per second, you can see it's essentially the same thing. So why would I even go and have somebody spend the extra time to do it? Well, it's a little more complicated. So I wanted to tell the story and kind of get through that in terms of what we did before into the fact that it was a little bit more complicated. So really in this scheme, what we were doing is we were running, or he was running 3 CCVs. So he was doing a low, mid, and high. And so that set of low, mid, high CCVs were run every 10 injections. So the queue essentially ran calibration blanks, this first set of low, mid, high CCVs, 10 samples, another set, 10 samples, another set, and so on down. So when you look at that, if you look at the concentrations and then you look at the signal and you're trying to essentially compare, look for trends, you can see to scan down through this data. Yeah, you can say, okay, I'm going from 0.5 to 1, and that's, should be about 2 times. And you can kind of do that. I'm not particularly that great at math, so for me, I don't prefer to do that. I mean, these are easy concentrations, but sometimes you're doing things like 12.5 or 7.5 to 12, and then it starts to become a little bit harder to sort of do that mental math and really look for trends. So in this case, the response factor is kind of where it really shines, right? So it should be the same. And assuming you're using a linear model that's where you're functioning in your method. And so you can see, I'm basically just looking, is this the same number or not? And so trends are really, really easy to spot when you use the response factor in this type of a situation. This is really a little bit more what we were looking at the time. Still yikes, still not what we want. So now what? So the big thing that really came out of this was the internal standard was not on the radar until we really looked into the data and looked at the response factors and did a little bit of the plotting and trending and things like that. So immediately, and based on some additional advice, a different, an alternative internal standard was actually identified and purchased. And there were some additional things to look at. Essentially the downward trend of the of arsenic, because unfortunately we can't have a we can't eliminate that from the method. That's required analyte. So there were some additional steps taken to figure out exactly what was going on there. And then the next big step was going to be to find a more appropriate internal standard and get back to that way of functioning where your quality controls work as they should. And so that is it for this story, and we can move on to some questions. Thank you. So welcome to the final story of the day. Unfortunately, this story is also about failing QCs. So let's go ahead and get started. So this is actually going to be based on pesticide analysis. So the method is up and running, validated, had been in service for some time, and then obviously things happen in the lab, something goes wrong, a batch was run, and then in the morning during data review, it became apparent that there were some failing QCs. So just a really quick brief, nothing too special about this method, LC triple quad, C18, pretty standard method. This was actually a multi-residue screen, so this was looking at about 160 compounds. Some of them were regulated, some of them actually weren't, and so we sort of had some limits we were concerned with, and then other compounds were more for screening. And this analyte listed includes some problem compounds as well. We used internal standards, about 6 of them. They were all isotopically labeled, and they were assigned primarily on